We'll be diving into the relationship between forces and momentum, and how this knowledge enables us to understand and foresee how objects interact with each other. So, let's get ready to explore the secrets of predicting the behavior of interacting bodies with forces and momentum. Here, we have a common situation: two billiard balls colliding on a table. We often encounter scenarios where objects interact or move together, and we'll be investigating how to predict their behavior during such interactions. Imagine you're playing pool with a friend, and the balls collide. How can we foresee their paths after the collision? That's where our knowledge of forces and momentum comes into play. Before we dive deeper, let's understand why predicting the outcome of these interactions can be a bit tricky. As we've all experienced, objects don't always behave as we might expect when they interact. According to Newton's first law, objects should remain at rest or move uniformly unless acted upon by external forces. So why do these objects behave differently during interactions, such as collisions or when they move together after contact? Before we move on, let me ask you, why do you think their behavior changes during interactions? Our central question for today is, how can knowledge of forces and momentum be used to predict the behavior of interacting bodies? Understanding this concept is essential because it forms the basis for explaining many natural phenomena and engineering applications. Before we unveil the answer, take a moment to think about how forces and momentum might influence the behavior of objects during interaction. Let's start with the basics. Forces are pushes or pulls that act on objects, causing changes in their motion. Forces can be categorized into two types: contact forces, like friction, which occur when objects touch each other, and action at a distance forces, such as gravity, which act even without direct contact. During interactions between bodies, forces come into play and influence their motion. The key is to understand how forces affect these interactions. Now, we come to one of the fundamental principles in physics, Newton's second law, which states that force is equal to the mass of an object multiplied by its acceleration F equals ma. This law establishes a direct relationship between the force applied to an object and the resulting acceleration it experiences. Newton's second law helps us quantify the effect of forces on interacting bodies, giving us valuable insights into how they behave during collisions or other interactions. Moving forward, let's talk about momentum, which is the product of an object's mass and velocity. The law of conservation of momentum states that in a closed system, the total momentum remains constant before and after an interaction. In other words, the total momentum of interacting bodies doesn't change, which allows us to predict their behavior based on their initial momenta. This principle forms the foundation for predicting how objects move during interactions and is a powerful tool in various physics applications. Interactions between bodies can result in two main types of collisions: elastic and inelastic. In an elastic collision, both momentum and kinetic energy are conserved. Objects bounce off each other without any loss of energy. In an inelastic collision, momentum is conserved, but kinetic energy is not. The objects stick together or deform during the collision, causing energy loss. We've journeyed through the world of forces and momentum, discovering how they enable us to predict the behavior of interacting bodies. These concepts are vital in explaining natural phenomena, engineering innovations, and celestial mechanics. I encourage you all to delve deeper into the fascinating world of physics, explore more on your own, and experiment with the principles we've discussed today. Thank you for joining me in this exciting exploration of physics. Remember, physics is all around us, and understanding it enriches our understanding of the world we live in. Happy learning!